All right, well, good morning, everyone. Welcome to Tokyo. I guess if it's your first time here, I hope you enjoyed your time so far. Welcome also to, I guess, our online attendees. I'm sure that some of you are, awake pretty late or awake pretty early, so thank you again for attending. So I'm going to tell you, a few things today. I'm going to talk about something that Blaine already mentioned, so artificial life, and I'm going to give you like a 1 minute, 2 minutes intro of what I think about A-life when people tell me about A-life as a field. Then I'm going to tell you about some of my research that has to do essentially with something that I think we could roughly identify as the problem of boundaries and the problem of agency. And then I'm going to try and tell you something about some of our recent work with Martin, the next speaker, and a couple of other collaborators, some of them being in Japan, some of them in Europe at the moment. So what do I mean by A-life? A-life is roughly the study of life as it could be. So we are interested in forms of life that don't necessarily abide by the rules of biology and life on Earth, but could be, say, could be following different rules on different planets. So it could be astrobiology that we talk about. It could be life in simulations. It could be life on some machines. It could be, different forms of life that exist in a completely platonic world as far as we are concerned. So what we are actually looking at is different forms of life, different forms of say, interesting systems that might even obey different types of physics. So we look at things that have to do with adaptation, autonomy, self-replication, self-organization, evolution, so on and so forth. Now, the interesting thing, is that in the last year or so, I've been engaging, I think, more actively with the AI safety and AI alignment community, and also throughout some of the, thanks to some of the meetings that Blaine mentioned. The first one for me was actually the one that my company, Araya team over there organized last year. So that's where I met some of the people that are also here today, some other people that then gave me other opportunities to engage with this field. And I would like to focus on some of the areas that I believe are common between research that we do in artificial life and research that is happening within the AI safety and alignment, I guess, space. So some ideas, agency, boundaries, things that I mentioned already, could be open-ended evolution. I think there is an interest in AIs that can actually learn to evolve and can actually, self-improve, learn a way to self-improve that could lead, say, to problematic situations. We are also interested in things like, meta-learning, so you could just call it perhaps like in context learning, at least in some situations, adaptivity or adaptability, evolvability, so, second-order functions, so like learning to evolve, learning to adapt, things like that. Today I will focus on boundaries, though. So the main difference that I would like to drive for now, and then probably bring back later during this presentation, is the fact that I believe there are two questions that are, equally as important, but that nonetheless should be considered different questions. One question has to do with what an agent is, and the other question has to do with what an agent does. Now, clearly they are related, but the point is that if you want to tell me what an agent is, you cannot start by assuming that there is an agent. So you have to first tell me what some kind of entity, individual is, and then some entities will be agents, some other entities will not be agents. A chair, hopefully, is not an agent. Most of the people in front of me right now, I would go as far as to say everyone right in front of me is an agent. So I want to be able to say that some objects are not agents, some objects are. Now, this is often, I would say probably not the case for some of the work that is happening in the AI safety space when people talk about agent foundations. There are exceptions. I'm mentioning Matt's work being some of the, a very good example of an exception. So people that are anyway studying what agents are, but in general, things are a bit different. Now, instead of, I guess, assuming that we have an agent, now there is there is also a surge in, interest in the AI safety space when people talk about boundaries as a key missing component. So here I'm particularly referring to this sequence of less wrong, but also to a smaller sub-community that is kind of growing. There was a workshop a couple of months ago in Berkeley. I'm going to be co-running another one next week on the mathematics of boundaries. So if you want, to go a bit further, what I mean by some of the differences here, there's also a difference in the kind of approach that people take when they ask one question or the other. Usually say for, if you want to ask what an agent is, you might want to start from something that has to do with a more physics-oriented framework. So we had dynamical systems, we have something maybe that has to do with information theory. But if you are ready to accept that you already are working with an agent, you might want to use something that is more oriented towards decision theory, some kind of utility theory, some kind of reinforcement learning. Now, what I will mention next is the sort of like big picture that I have in mind. So there are fields where agents is like the main thing. We kind of assume that agents are there. We don't really ask what they are. If we are doing sociology, if we are doing psychology, if we are doing economics, if we are doing to a certain extent computer science, we kind of assume that agents are a thing. We don't really question that. Now in some other fields, we don't really even bring out the idea of agent. So if we are doing some kind of physics, if we are doing some kind of geoscience related research, we don't really hear a lot about agents in those areas. And I would say A-Life is something that tries to be in the middle. We try to find like the minimal notion of agency that would make lower level, in some sense, interested, and higher level, at least like engage with our own definition. To this extent, I will now go into some of the work that I've done before, some of the other work that was in the title that I think well captures this distinction that I'm trying to drive through. So there is this idea, this framework called the free energy principle, originally coming from neuroscience, and that recently has taken off also in the alignment space. This is a proposal for what an agent should actually be. So the proposal is something like, well, if a system minimizes this particular cost function that we call free energy, that's an agent. The key part is something called Markov blankets that I will be talking about soon. We then have something very related to this, and usually these terms are used interchangeably, but I want to be clear that I believe they are quite different. There's something that is like the principle that I mentioned before, and then there's something that is called active inference that is also coming out in the alignment space more recently that has more to do with what agents do. So how do they make decisions? How do they come up with policies that actually achieve certain goals? This is a bit of a punch in the face, and I'm not going to go through all of the details. I'm just hoping that this will be useful to somebody if you ever have to go through these slides again. This is my sort of summary of what this free energy principle is supposed to be about. This is coming from 3 years ago, but as far as I can tell, the main arguments are still the same. My point here is just I will be talking about a specific thing, these Markov blankets, and then I will be saying, I guess, a few things about those and how I think we can actually move beyond them. So Markov blankets, so these are simple notions that come from the literature on graphical models. So here I have a simple example. I have a bunch of variables, a bunch of nodes. These are all random variables. Here I just want to say that x and y are conditionally independent. given the variables in the middle. The variables in the middle are what people call a Markov blanket. If you are familiar with this separation criterion, well, here we are. There are other examples that I'm not going through in detail here, but I just want to drive the idea that there's something like, having a boundary, having some sort of like veil that separates something from something else. This is why people are kind of excited, I guess, about this idea. Now, in a paper that we published a couple of years ago now, we tried to make sure that, certain things were clarified, so we came up with a distinction. You might not perhaps like the names that we use, but again, I think there's a distinction that actually makes a difference. So there is something that we think is just the classical notion of Markov blankets, how I think Judea Pearl first called them in his book, 89. And then there's something that we think actually came out from this free energy principle literature. The former, I guess, has more to do with veils where we have random variables, but we don't really specify a notion of time. And then the free energy principle version tries to say something about stochastic processes, so time index random variables. And so now we have time series, and we want to understand conditional independence for variables in a time series. Now, there's some philosophical, take that usually people have with one or the other, but I guess that what I want to really go towards is the fact that for Pearl blankets, for the original notion of Markov blankets, there's no claim that they actually define the thing that actually is conditional independent on some other thing. But this free energy principle is trying to tell us that no, the Markov blankets that they use, these Freestone blankets, actually tell us what an agent is. And we'll, is that really true? Well, we'll see. So this is why I'm mentioning, active inference on one side. We can do decision making. We can say we are doing inference with some Markov blankets, approximate method, amazing. But then there's also a thing that is like, no, we actually have a theory of what an agent is. And those are two very different claims in terms of strength, in terms of technical effort. So I'm going to be focusing on a couple of things. Again, I'm not really going through some of the philosophical side and some of the other stuff that is also interesting, but not particularly here. So the first thing that I'm trying to, bring out is the fact that if the notion of a veil, if the notion of a boundary is kind of well defined and easily understood without time being a variable, that is not necessarily true when you have time. So if we have a bunch of time series, like in this case, I just had 3, but there are various connections there, it's less clear exactly what is supposed to be independent of what. So is it an entire time series? Is it a node? So is it a particular, say, node at a particular time? Is it like a bunch of nodes like at different times? It's not really clear what the entity is supposed to be here. Do we want a notion of agency that is time independent? Well, that's not trivial. Do we want a notion of agency that only exists at a particular time? Well, that may also not be what many people are interested in, because I think that most people identify as being themselves over time. Now, this is something that has been brought out by different people, including Martin, the next speaker. And, I tried to summarize, again, another punch in the face. I'm not going to go through the details. The point is that I've seen at least 6 or 7 different ways that people have been talking about Markov blankets that are very different. They make different assumptions. Some of them work with time, some of them don't. Some of them assume that, there are stationary distributions, some of them don't. Some of them include the past but not the future. There's a lot of stuff going on. So just labeling everything as a single entity, this Markov blankets thing, will not do the job. Now, another, I guess, possibly like the main issue, I would say, or the main potentially, or the main area, I guess, that might have something for us to investigate, is the idea that, you know, if you want to have a theory of agency, a theory of something that tells you whether there's an agent that makes decisions, good or bad, you'd like to do that in a way that is, you know, as agnostic as possible. If you have to go into a system and tell me what the boundaries are yourself, then you're not really identifying an agent. You're just identifying your bias for that particular system. In some cases, this is a very good idea. Like if I build a robot, I think I have a very good notion of where the boundaries of the robot are, modulo some exceptions. But if I have some really complicated black box system, some LLM, how do I know that this system is not actually expanding on the internet, copying itself on some different system without me knowing, and I'm still looking at the same machine, thinking that there's an agent there, and this thing has moved on. This is not how, you know, this is not how we want to identify agents. We want to make as few assumptions as possible. And is this happening with this free energy principle? Well, kind of not happening. So we have some Bayesian network. So we then go and say, oh, we are interested in a particular variable or a particular set of variables. Notice that I'm not bringing out time again because time is complicated. So I'm trying to give you the general picture. If you add time, it's even more complicated. We identify some variable. We say this is the variable that we are interested in, and then we try to find the Markov blanket. Well, if that's the case, then, you know, is this really a theory of agency? I'm not sure. Like, if you had to select some variables of interest, it means you already had some notion, some bias towards those being important. And maybe that's fine, but then this is not a theory of agency. So there are then other issues, potentially, like, you know, there's a case that I didn't actually go through when you identify some Markov blankets. You have this case with a head-to-head, or also, you know, the case, I think it's called also the collider case, where you have two variables that are pointing to the same thing. If you select one of the top ones, one of the parents as being the variable of interest, the other one also must be part of the blanket. Now, it's quite easy, and we did this like in this paper, to come up with cases where the other parent is evidently something that, you know, is carried out by a different system, something that you would like to call an agent. And I'm not sure that that actually needs to be part of a notion of a boundary of some agent. I don't want, like, you know, Blaine's leg kicking my knee being part of the boundary of me as an agent. All of this to say, there's a theory of agency, there's a theory that is just about some decision making. It's not just. There's a theory that is about some decision-making rule with different cost functions, different algorithms that people are also interested in the AI safety space, this active inference stuff. That's fine. If it works, I'm very happy. I think all of my focus was on the other side, so the theory of agency stuff. Once again, like sort of a bigger picture, what an agent is, things like this free energy principle, maybe not. Some of the stuff that Martin will be presenting next, some of the work that me, Martin, and other people are doing, some of the boundaries work that is happening at the moment. And then there are, you know, theories of what agents do, reinforcement learning, some decision theory, framework, game theory, so on and so forth. With the last, I don't know, like 1 or 2 minutes, I will just try to go through like some very, you know, high-level story of some of the work that I'm doing with Martin, and then I'm hoping that it will actually cover some of the big holes that I'm going to inevitably have. So we are interested in agents. I think you got this by now. We are interested in agents of different kind. It could be in AI, but it could be also in other areas. So let's try and understand what it means for an agent to have some interaction with an environment, and let's use this notion of interaction to actually understand agent and environment themselves. So this is an idea to say, if you start by defining what an agent is, and then tell me that the environment is the complement, and then they somehow interact, well, that's great, but that may not be the entire story. There are very easy cases where I can show you that by starting with an interaction, I can get agent and environment, but I cannot necessarily go the other way around. So in this case, we just took like some idea where we are saying, well, let's take this blob and let's say that an agent and an environment are in a good interaction if they are inside, but not if they're outside. Well, there's this notion of internal model that comes from control theory, where we basically say, well, let me skip to the next slide because that's basically the point that I want to drive through anyway. There's this notion of biosimulation that is essentially some relation between two sets that preserve structure over time. So we want to try and represent some notion of interaction between an agent and an environment in terms of something that it could be a biosimulation or some generalization of, where we say, well, there's this particular relation, and this relation needs to preserve the interaction between agent and environment over time. What does that mean? Well, it means that we have some, that we are identifying agent and environment as dynamical systems that have some specific laws that preserve certain, interactions in a lawful way. So this also has to do, and this is the part that I will hopefully, where I can hopefully rely on Martin, giving us all a better intro. This has to do with something that is also related with the with Bayesian inference, with the idea of agents having a model of their environment, as in trying to understand the causes, trying to understand the states that are generating certain observations. And here, again, like a bit of a punch in the face, we can actually define some notion of consistency between agent and environment that probably has to do with biosimulations, but it's a bit unclear still. And this thing will actually turn out to be some form of Bayesian inference. And this is the part that I'm hoping Martin will actually cover. So to end, I guess, the talk, green, good stuff. Yellow, not sure. Blue, to do. Green stuff, so I think there should be more interaction between the A-Life field and the field of AI safety and alignment. I think some stuff is already happening, more could. Free energy principle for AI safety, not sure. Active inference for AI safety, possibly. We just have to, show it working. Other areas, I guess, that I'm interested in, so abstract notions of models, systems that actually model other systems, world models, so on and so forth. There's stuff that we are doing with Martin and other collaborators that I think will be relevant, but again, to see. Thank you.
Ude, while I rescue my microphone, do we have any questions from the audience? Yes.
Thank you for the talk. You are saying that free energy principle for air safety, well, unclear status. Why?
Why it's...
why is it's not promising while active inference is marked as to
Yes,
do?
so I would say my take is that the free energy principle is trying to be a theory of agency, and I don't think it is, because you are selecting stuff and then you're telling me, oh, this is the Markov blanket of the stuff I selected. But if you're selecting stuff, it means that there's something outside of this, say, theory or this principle that is allowing to make that choice. Like, this is the stuff that I'm interested in. And I would say that's outside the free energy principle. Then you can apply the free energy principle and you will get something interesting, perhaps. But what makes you say that this is the interesting bit to investigate? Active inference, it's some, I'm a bit oversimplifying, but it's something like reinforcement learning with a different, cost function and maybe like different algorithms that implement like the optimization of this cost function, like some reward maximization like thing. And yeah, I think that's possible. Like, in that case, there's no claim that that's a theory of agency. It's more like a theory of, yeah, an alternative to reinforcement learning. And I think that's a very, worthwhile direction. Like if it works, I'm very happy. Theory of agency, free energy principle, I'm skeptical. I don't see that being a theory of agency. I don't know if it helps.
Thank you. Can we move one row back?
Thank you for your presentation. So I've been working in active learning with Bayesian optimization for a few years, and I haven't thought about this theory, so the theory of agency. And I was wondering, this is a really simple question because I don't know a lot about this, but I don't really understand what will be the link with the theory of understanding the theory of agency and the AI safety. Is it some link that if we just understand that we have a thing or an agent somewhere, then we can just, we will be able to determine what is the problem and things like that? Or, yes, so this is just my question.
Yeah, so I would say the systems that have agency are fundamentally different from systems that don't have agency. So let's say, it's not probably the best example, but if I build a robot and I implement like some algorithm for this robot to do stuff, things can still go wrong because it will be implemented it will be embedded. It will be in the real world, things can go wrong. But I would expect that a system that actually is an agent and can actually make decisions for itself, change its goals, be autonomous, will have a whole different class of things that could go wrong. So it could be like, I think I mentioned a bit, perhaps ambitiously some example earlier. Let's say that, I have some LLM that is implemented on a machine right in front of me, like, this is where I trained it. And now it's actually, implemented and giving me inferences about stuff. And now I think that's an agent. Now, if it is an agent in the sense that I think it could be an agent, as far as I know, it could have replicated itself on a different machine somehow. Like, it could have convinced a different person, oh, yeah, you should connect me to the internet and I should copy myself somewhere else. And I will still look at this machine thinking that the agent is there, when it could perhaps just be like some empty shell of something that has moved somewhere else. Yeah. So in some sense, I think we often assume that, yeah, the agent is there because that's where I see it, but then maybe it's not, or maybe it's just a shell of something that is somewhere else.
Yeah, so the problem is basically on the assumption we decide.
Yeah, yeah. I think it often works, but I think it doesn't always.
Yeah, that sounds to be a really complicated thing to do with minimal assumptions.
Yeah. But Martin is coming up next. Okay, a lot of pressure now, Martin.
Thank you so much.
Well, we have time for one more before Martin's talk. Perhaps from Shun at the front here. Keep your hand raised, please.
Thank you for wonderful talk. Autonomy is essential to AI life, but some of the AI life researchers argue AI alignment research try to suppress autonomy.
Yeah.
What do you think about this argument or contradiction?
Very, very good point. So I would say there's clearly an interest in autonomy in, say, AI life, and there's, as you say, an interest in autonomy in AI safety, and they seem to be like, different, probably like perspectives. We kind of want to understand what it is and maybe implement it, and then there's, the risk of actually having an autonomous system that could actually drive us to not want it. So I think the most agnostic position that I think we are taking is that we need to at least understand what autonomy is. And then whether you want to implement it, like on some crazy system or whatever, well, there should be regulations against that. And whether you don't want to implement it, well, at least you should know what not to implement in some sense. Like, if we have some, I guess, notion of autonomy that we kind of agree on, as in we implement this algorithm and the system will become autonomous, then there's decision making to be done there that is, I would say has to do more with policy making that with the research itself on autonomy. But I would say, yeah, we anyway need to investigate. I want to understand what autonomy is. And then I'm very happy to not have autonomous AIs, I think, yeah.
Thank you.
Okay. Thank you, Martin.
Thank you.
Sorry, Manuel. And I would like to welcome Martin.